Hello friends, in my previous video we have seen the circuit diagram of Wien-Bridge oscillator. We derived the expression of the frequency of oscillations of the circuit and the stability issues with Wien-Bridge oscillator. Now in this video we will be talking about the next oscillator, that is the phase shift oscillator. In phase shift oscillator, the general block diagram of the oscillator is this, where we have a forward path. This is the forward path where we have an amplifier, and this is the feedback path where we have a phase shift network, which is a feedback network. So this is the feedback network. So here the main function performed is the function or operation performed by this phase shift network. Remember, in general, oscillator consists of an amplifier which may be providing us the phase shift of 180 degree. In inverting mode of an amplifier, maybe operation amplifier, maybe common emitter configuration of BJT, maybe common source configuration of a MOSFET, there is phase shift of 180 degree from input to output. So this is the amplifier, which is basically an inverting mode amplifier, which may be op-amp based amplifier, BJT based amplifier, or MOSFET based amplifier. So when signal goes from here to here, it gives me the phase shift of 180 degree. What is the meaning? Suppose this is the signal I have at input. So when it reaches at the output, you will find 180 degree phase shift. So this positive becomes negative and negative becomes positive. So that is 180 degree phase shift provided by the amplifier, which may be inverting mode op-amp, common emitter, BJT, or common source MOSFET based amplifier. Now remember, as per Barkhausen's criteria, when signal from output side comes back through feedback network at this input point again, so that signal should be again in this format, so that I have this signal at the output again. So that means this negative should become positive when it comes here, and this positive should become negative when it comes here. That means this feedback network must provide a phase shift of 180 degree, right? So for provision of 180 degree phase shift, we have three RC circuits: first, second, third. Remember, a capacitor provides a phase shift of 90 degree maximum, or we can say a 90 degree. But when you have resistance in combination with capacitor, it cannot provide the phase shift of 90 degree. So we make adjustment of C and R in such a way that it provides the phase shift of 60 degree. So for the provision for having phase shift of 180 degree, I have three RC circuits connected in cascade, so that total phase shift is 180 degree. So what I mean to say is, the phase shift network have three RC circuits connected in cascade for getting overall phase shift of 180 degree. Therefore, each stage of RC circuit has phase shift of 60 degree. This is one objective type question which may be appearing in different competitive exams like engineering services, right? So here I have to derive the expression of frequency of oscillation, number one. Two, I have to find the condition for this circuit, condition of oscillations. So we will see that condition as well. So let us proceed how to find the frequency of oscillation. First, I have to analyze this feedback network. So for analysis of the feedback network, remember, feedback network gives me what? Feedback network gives me the feedback factor. So what is that feedback factor? Remember, the feedback factor is nothing but the ratio of feedback voltage divided by output voltage. And what is A? A is nothing but your output voltage divided by input voltage, which is feedback voltage here. So A is Vf. What I mean to say is product of A beta should be 1 as per which criteria? As per Barkhausen's criteria, right? So A beta is 1. Fine. Now my aim is to get beta equal to this from this circuit. So we will try to find the expression of beta here, that is the expression of feedback factor. So let us see one by one how to get the feedback factor for this feedback network. So for getting feedback network, so I will be using I have to find the ratio of Vf by V naught. How to find that Vf by V naught from this RC network? There are two tools, KCL and KVL. So when I have three nodes here, this node gives me feedback voltage, so I can make use of KCL. That is simple network where I have three nodes, so I can make use of KCL. You can make use of KVL as well, but that will be studied separately in electrical circuits, where to use KCL, where to use KVL. So I have three nodes here, I can make use of KCL for finding the ratio of Vf to V naught. So let us see how to find this feedback factor beta for this network. So I will be applying KCL at different nodes one by one, and this expression, whatever I am going to do here, that becomes important question for university exams and for engineering services and civil services mains exams, right? So applying, now let us proceed, applying KCL at node A. So when you apply KCL at node A, what do we get? VA. Now when you apply KCL, so how many nodes are, how many branches are connected here? This and this. There are three branches. So current in this branch is VA minus V naught by this impedance. Or you can say reactance of capacitor. So VA minus V naught by reactance of capacitor is what? 1 by j omega C. Then current in this branch, that is VA upon R. Then current in this branch, that is VA minus VB upon 1 by j omega C, that is reactance of capacitor, right? So I can simplify this like this, that is 1 by R plus j omega C into VA plus what? J omega C into VB plus what? That is V naught, that is j omega C into V naught, that is equal to 0. Or you can modify this equation further, that gives 1 plus j omega CR into 2 multiplied by, that is 1 by 1 plus j omega 2 omega 1 plus j 2 omega CR into VA plus j omega CR VB plus j omega CR into V naught, that is equal to 0, and there has to be minus sign here, not plus. That is the simplification of this equation only. Minus, this is also minus. Fine. So say this is equation number 1. That is equation number 1. Now apply KCL at node B. Apply KCL at node B. When you apply KCL at node B, what do we get? VB minus VA by 1 by j omega C. What is this current? Current through this branch, that is remember, whenever you apply KCL at node particular node, all the currents are assumed to be outgoing. So current in this branch will be VB minus V upon this. Current in this branch will be VB by R. Current in this branch will be VB minus VC upon 1 by j omega C. So this gives VB upon R plus VB minus VC. And what is this VC? Voltage at node C is what? Voltage at node C is nothing but voltage Vf, that is feedback voltage. So VB minus Vf by 1 by j omega C. This is equal to 0. You can modify, you can simplify this equation now. That gives what? Minus j omega C into VA plus what? That is 2 1 by R or 1 by R plus j 2 omega C into VB minus j omega C into Vf, that is equal to 0. Or you can modify this equation further, minus j omega Cr into Va plus 1 plus 2 j 2 omega Cr into Vb minus what? Minus j omega Cr into Vf, that is equal to 0. That is equation number 2. This is equation number 2. So, I have got this equation and this equation. Remember how many nodes are there? There are 3 nodes. So, there will be 3 equations, there will be 3 variables, but I have to find relationship between this variable and that is variable Vf and V naught. So, I have to eliminate one variable, that is voltage at node B. So, by eliminating voltage at node B, I will be able to find the relationship between, or we can say by eliminating voltage at node B and A, I will be able to find the relationship between these voltages, right? Now, let us see, let us proceed further. What will be current in this branch? Remember, current, input current of op-amp is assumed to be 0, or we can say input current of amplifier is assumed to be 0, or analysis I am doing is this, right? So, this is assumed to be the input impedance of amplifier is assumed to be very high, and current drawn by the amplifier is assumed to be negligible. This is what I can say. So, I am analyzing this by simply considering that these are open, fine. So, now I am neglecting current in this branch for this analysis for finding the feedback factor, right. So, now apply KCL at node C. Applying KCL at node C. When you apply KCL at node C, what do you get? Voltage at node C is nothing but Vf. So, Vf upon R is current in this branch. This current is neglected, I have already explained. And what is current in this branch? That is Vf minus Vb upon 1 plus j omega C, that is equal to 0. This is what you have. So, that gives what? That gives me the relationship between Vf and Vb. So, we get Vf j omega C plus 1 by R into Vf, right, minus j omega C into Vb, that is equal to 0, fine. So, further you can simplify, that gives me Vb in terms of Vf. So, Vb will be equal to what? That gives me 1 by j omega C. So, 1 plus j omega Cr by j omega Cr into Vf. So, what I did? I have simplified this equation. So, that gives me the relationship between Vb and Vf, fine. So, how to get this? So, you can take simply R here and put R here, and then you can find that relationship. So, Vb in terms of Vf. So, that is equation number 3. That is equation number 3. So, by putting this relationship maybe in this equation, I am able to get relationship between V naught, Va and Vf, right. So, let us proceed further. Putting expression of V, that is expression of Vb in equation 1, we will be getting that relation. Putting expression of, that is putting expression of Vf, not Vf, Vb in equation 1, we have, what do we get? Let us see. When you put that relationship here, I get 1 plus j omega Cr into Va plus, you please see, what do we get? You put that expression here, so I get minus 1 plus j omega Cr into Vb minus, not Vb, that is Vf. So what do we get? That j omega Cr is in the denominator here, so when you put that expression here, so j omega Cr get cancelled, so that we get only numerator component here. So minus what? J omega Cr into into V naught, that is equal to 0. So this is equation number 4. Fine. So my ultimate objective is what? My ultimate objective is to get relationship between, that is V naught and Vf. So see this equation. Here I am able to get the relationship between Va, Vb and Vf, right? So if you put expression of Vb in this equation, what do we get? So putting the expression of Vb in this equation. So let us see how to proceed. Putting expression of Vb in equation putting expression of Vb in equation 2, putting expression of Vb in equation 2, we have, what do we have? Minus j omega Cr into Va plus 1 plus j2 omega Cr into Vb. Vb is what? That is 1 plus j omega Cr by 1 j omega Cr into Vf minus j omega Cr into Vf. This is equal to 0, right? So by putting expression of Vb from this equation, I get this relationship. So let us proceed further. You can simplify, you can modify this. So we get minus j omega Cr into Va plus, or you can multiply, or you can simplify it like this: 1 plus j omega Cr into 1 plus j omega 1 plus 2 omega Cr minus, you multiply this, so you get plus omega square C square R square into Vf divided by what? Whole divided by j omega Cr. So what I did, I have taken LCM here, right? So this is equal to 0. So this is equal to 0. I have to get expression of Va in terms of what? In terms of Vf. So from this equation, I get the expression of Va like this, that is Va equal to 1 plus j omega Cr into 1 plus j omega 1 plus 2 1 plus j2 omega Cr minus or plus omega square C square R square whole divided by. Now when you take this on the side, I have minus sign here, omega square R square omega square C square R square into what? Vf. So what I did, I have taken this on right hand side, or we can take this on right hand side. So you will be able to get relationship between Va and Vf. So this is equation number 5. So when you put expression of VA in this equation, so you will be able to get expression of V naught. So put from equation number 4 and 5 we have. Now you can proceed. So that gives 1 plus j 2 omega CR into 1 plus j omega CR into 1 plus j omega j 2 omega CR plus omega square C square R square whole divided by what? Omega square C square R square. Here I have minus sign. So we have minus sign here as well. So this gives expression of a relationship between Vf and V naught. So let us proceed. So minus what? That is 1 plus j omega CR into Vf plus this, sorry, minus this. So this gives me equal to j omega CR V naught. Fine. So I have taken this on right hand side. So that is how we get overall expression of V naught in terms of Vf. Fine. So let us find the further simplified expression between, that is expression for relationship between Vf and V naught. So let us proceed. So into Vf here, into Vf here, minus. Fine. So I have to find what? Beta equal to, that is Vf by V naught. So when you take Vf by V naught, so j omega CR I have multiplied by omega square C square R square whole divided by, that is whole divided by what? 1 plus j 2 omega CR into 1 plus j omega CR 1 plus j 2 omega CR plus omega square C square R square, right? That's what you have. Fine. Then further minus, sorry, plus, not minus, in denominator itself, that is 1 plus j omega CR multiplied by omega square C square R square. That is what you have. That is denominator. So this expression can be further simplified like this: j omega cube C cube R cube divided by, you get 1 plus j 2 omega CR into, now you simplify this, you get 1 minus, when you multiply this, so what do we get? 2 minus 2 omega square C square R square. We have omega square C square R square here, so we get only one term containing minus omega square C square R square, and multiply this and multiply this, you get 3j 3 omega CR. This is simplified expression. Then plus 1 plus j omega CR into omega square C square R square. That is simplified expression. So further you can further simplify it like this: j omega cube C cube R cube whole divided by, now you multiply these two, you get 1 minus omega square C square R square plus j 3 omega CR. What I did, I have multiplied this one to this factor and then multiplied this factor to this complete factor. You get plus j 2 omega CR minus j 2 omega cube c cube r cube, multiplied to this, you get this, multiplied this to this, you get this, multiplied this to this, you get what? Minus 6 omega square c square r square, and multiply this as well, plus omega square c square r square, and what? Plus j omega c cube r cube, omega cube c cube r cube. Now beta can be further written like this, j omega cube c cube r cube. Now what are the terms containing real values? This is real number, so this and this is cancelled, so I get 1 minus 6 omega square c square r square. That is one term I have. Then terms containing j, I have j into 5 omega c r, what? This plus this is added, and then I have minus 2 omega square, minus 2 omega cube c cube r cube, I have plus j omega cube c cube r cube, so I get minus omega cube c cube r cube here. That is the simplified expression of beta. Now if you remember the Barkhausen's criteria of sustained oscillations, the product of A and beta should be what? Equal to unity. The overall loop gain of the circuit must be equal to unity. That is what the Barkhausen's criteria says, right? So here I'll rewrite that. Here the product of A and beta should be equal to 1. Normally it is assumed that the gain of the amplifier is a real number. We are assuming, we are neglecting the frequency effects on the amplifier. We are talking about mid-band gain, right? So that means I am assuming I am having the frequency of oscillation which is lying in the mid-band of the amplifier A. So when A is real, the product will be real only if beta is also real. But now see this expression. In this expression, numerator is imaginary, denominator has real as well as complex components. So this is real, this is imaginary, so real as well as imaginary components. So this becomes real if denominator is also imaginary, and denominator becomes imaginary if this is 0. So for, or we can say beta is real if what? 1 minus 6 omega square c square r square is equal to 0. I repeat, beta becomes real if the real part of denominator is 0, because j and j will be cancelled out, right? So that gives omega equal to 1 by under root 6 r c. This is the expression of frequency of the oscillator. So that gives me only at this particular expression of frequency beta is real and this product becomes equal to unity. So that becomes 1 by 2 pi root 6 r into c. These expressions are very important as far as exam is concerned. So from here what do we get? Omega square is equal to 1 by 6 c square r square. Fine. So now you will find this, you should remember this expression because there can be objective type questions in GATE, in engineering services prelims, or in any PSU exams. But I am driving this expression because that becomes important for civil services mains and engineering services mains as well as university exams. Fine. Now after getting this expression, beta has become real, and what is the real value of beta? Let us see that. So when this is 0, so j and j is cancelled out. So I have omega cube c cube r cube in the numerator, and what will be there in the denominator? 5 omega c r minus omega cube c cube r cube. So omega c r will be cancelled from numerator and denominator. So we get omega square c square r square divided by 5 minus omega square c square r square, right? So now you put expression of omega square from this equation into this. So when you put expression of omega square equal to 1 by 6 c square r square, I get the value of beta. So that gives me what? That is 1 by 6 c square r square multiplied by c square r square divided by 5 minus 1 by 6 c square r square into c square r square. This is what you have. So c square and c square get cancelled out. So I get beta equal to 1 by 6 in the numerator, 1 by 6 in the numerator divided by 5 minus 1 by 6 in the denominator, and that is nothing but 1 by 29. So the real value of beta for sustained oscillations of the circuit is nothing but 1 by 29. This is very important. You have questions in exam. So yeah, now you, for sustained oscillations, what is the condition? For sustained oscillations, what is the condition as per Barkhausen's criteria? That is this condition. So A into what is the value of beta for sustained oscillation? 1 by 29. So 1 by 29 should be equal to 1. So A should be equal to 29. This is very important. But remember, for sustained oscillation, it should be greater than or equal to. It should not be less than 1, or either equal to 1 or little greater than that. So if you put that condition, you will get A should be greater than or equal to 9. So that means minimum value of the gain of the amplifier should be 29. This is again very important. You have small objective type questions in maybe in GATE or engineering services prelims. So this is a factual question, but you should remember that. Small questions can be there from this value or from this value or from this expression. There can be numerical based on this expression as well. So this is the overall mathematical analysis of phase shift oscillator based on the simple phase shift network connected in the feedback circuit, and that phase shift network is simply RC network here, right? So there can be different circuits connected in feedback network, but when you talk about RC phase shift network, we have 3 stages of RC network as given here, right? So now the question comes, what is the type of amplifier connected in forward path? The type of amplifier. So we will talk about the different types of amplifiers connected in the forward path of phase shift network, right? So let us see what could be the different possible amplifiers. Fine. So here we have 3 possibilities. First, I will be talking about op-amp based phase shift oscillator. When you have op-amp based phase shift oscillator, that amplifier is nothing but op-amp based amplifier. And what could be that amplifier? That is very simple. I have to connect that I have to connect phase shift amplifier, I have to connect that op-amp based amplifier in inversion mode. Why? Because this network provides me the phase shift of 180 degree. So I connect an amplifier, op-amp based amplifier in inversion mode. That's it, right? So I have this type of circuit. This is output voltage V0. This is input which is connected at the feedback network. This is input terminal, this is output terminal, this is minus, this is plus. Why? Because I have to connect this in the inversion mode to get 180 degree phase shift from input to output, because this network is also providing me the 180 degree phase shift. So only then there will be net shift in net shift in phase of the signal will be 0. 180 this will be inverted, so 0 in total phase. Because as per Barkhausen's criteria, the total phase shift in the loop should be 0 degree or means 180 or 360 degree, that is same thing. So this is R1, this is RF. So this is that amplifier which was shown, right? So what will be gain of the amplifier? gain of the amplifier will be 1 plus RF by, not 1 plus, I'm sorry, this is inversion mode, so this is minus RF by R1, that is gain of the amplifier, that is gain of this amplifier. Beta for the network we have already seen, that is 1 by 29, right? The product of A and beta should be, I'll be talking about magnitude, so that should be greater than or equal to 1. So what will be magnitude of A? Magnitude of A is RF by R1, right? So what do we get? We get RF by R1 into 1 by 29 is equal to 1, right? So RF is equal to how much? RF is equal to 29 R1. That is the condition for this circuit to work like an oscillator. So there has to be relationship between RF and R1, that has to be this relationship. Fine. And of course frequency of oscillation for the circuit we have already seen, that is driven by this feedback network, which was 1 by 2 pi under root 6 into R into C. So this is the frequency of oscillation, and that is condition for sustained oscillation. RF, that is feedback resistance, should be 29 times, at least 29 times the value of R1. So that is one simple circuit based on op-amp based amplifier. Similarly, I have amplifier which can be based on MOSFET, that is second one, that is MOSFET based amplifier. In MOSFET based amplifier we have simple MOSFET based circuit. Maybe I have MOSFET here like this, right? So in MOSFET base, of course you have to connect an amplifier which is simply based on MOSFET circuit. So I have a resistance here, I have capacitor here, this is grounded, this is source resistance, this is source bypass capacitor, I have a resistance here, maybe RD, this is RS, I have biasing voltage, right, and this is connected at the input, and this is nothing but output terminal of the MOSFET, this is V0, right. The circuit remains similar, this is gate terminal, this is drain, this is source. So this is your simple circuit based on MOSFET amplifier. So I have to connect an amplifier in forward path, that's it, right. The conditions remain same. I have, of course, by using small signal analysis of the circuit, we can definitely find the gain of this amplifier. So that expression is not required here. You can go for analysis of the MOSFET, that is small signal analysis of MOSFET based amplifier, but condition remains similar here, right. So what is minimum gain? What will be the minimum gain here? The minimum gain of, I repeat, from this feedback network we have seen beta is this, so A into beta is equal to 1. So beta A is equal to 29, less than or equal to, you can say like this, as per Barkhausen's criteria, less than or equal to I am saying. So A should be, minimum value of gain should be 29 for MOSFET based amplifier. So if minimum is 29, you can find the value of gain A for this amplifier, and of course you can proceed further, right. How to find gain? I repeat, you can go for mathematical analysis. I have, for analysis what do we do? This is bypassed, right. So this is nothing but your small signal model of the MOSFET, right. This will be connected to the ground here, this is grounded, right, this is RD, this is supply voltage is grounded, this is small signal equivalent, right. So this is feedback voltage, that is feedback voltage. What is this? This is GM into, this is current, so GM into this voltage V, that is VF. So this current is nothing but drain current, which is equal to transconductance of MOSFET into VF, and this is RD, right. So this current will be passing through this. So what will be the gain? Gain of the amplifier will be nothing but minus, or we can say what will be output voltage of this. So this current will be passing, going this way, so this is plus, this is minus, so output voltage will be minus GM into RD into VF minus sign. So gain for this will be minus of V0 upon VF, sorry, plus, that will be minus GM into RD. That is gain of the amplifier. Why I am doing so fast? Because we have seen the analysis of the MOSFET based amplifiers. I can find the gain of the amplifier by replacing BJT, by replacing MOSFET by its small signal model and replacing biasing signals by ground. So that is how I can find the gain, and that condition can be obtained. But I am not going into that depth because you don't have those type of questions. But if there are questions, you can analyze this way, right? Fine. So that is what you have. Now, in gate, if there is a question, you can simplify that way. Fine. Third case is, that is BJT based phase shift oscillator. That is BJT based phase shift oscillator. So in BJT based phase shift oscillator, this amplifier is replaced by BJT amplifier. Fine. So how to replace that amplifier by BJT amplifier? I have a simple potential divider network, right? We have BJT like this, right? So this is BJT based amplifier, where your amplifier is nothing but simply BJT based. This is RC. We take feedback from here, right? And this goes to feedback network, and then this is connected to input of the amplifier. This is R1, this is R2, this is RC, this is RE, and you can connect capacitor by, that is ammeter bypass capacitor here. That amplifier is now BJT based amplifier, and overall circuit is called BJT based phase shift oscillator. Now there is small change in feedback network of BJT based oscillator. This resistance here is not connected in shunt, rather it is connected in series like this, right? R dash, and this is input impedance of the circuit. So this R dash is equal to value of R minus Zi. That is the expression of R dash in BJT based amplifier. Fine. So in BJT based amplifier, I have R dash, that is R minus, R is with this one. So now what is Zi for this circuit? That is equivalent impedance of the amplifier, and equivalent impedance of this amplifier is nothing but when you connect this in parallel with this. So I have R1 in parallel with R2 plus HIE. That's what you have. That will be the overall impedance of this network. Fine. That's in parallel, not series. That will be in parallel. Why? Because impedance seen on this side will be HIE, and when you replace the BJT by small signal model, so the equivalent impedance would be R1 in parallel with this R2 and in parallel with HIE. So that is approximately equal to HIE. That's approximation. And how I am doing this? Because you can see the small signal analysis of BJT based amplifier. From there I am writing this expression. Fine. So the input impedance, in that case, what will be R dash? R dash will be equal to R minus HIE. This is approximate expression. As such, you never had a question on this. I am just covering for the sake of coverage. Now there is one important expression you should remember here, the expression of frequency for this oscillator. Because R dash is connected here, the frequency of oscillation for this oscillator is 1 by 2 pi under root 6 plus 4k. So in place of root 6, which was in op-amp and MOSFET, it is 6 plus 4k multiplied by RC. Now what is this k? K is here, where k is ratio of RC to R. Fine. This is important. There can be question in engineering services prelims. This is important. That ratio is important. Fine. This is, so in place of Why? Because of this introduction, this change in the phase shift network. Because of that, I have change in frequency of oscillator for this circuit. You should remember, because the complete analysis is not required, but you should remember this expression. Fine. So this is overall expression of frequency of oscillation of BJT based oscillator. Fine. There is another important relation you should remember for BJT based amplifier. The gain of the BJT HIE should be greater than or equal to, that relationship here is 4K plus 23 plus 29 by K. That is another relation you should remember. Again, this is purely for the engineering services prelims. These are factual. For engineering services, you should remember all the expressions directly. You should not go for mathematical analysis. For mains, I don't think there will be any question on based on BJT base. There is rare possibility that you have question on this directly, right? So another important thing, HFE is minimum for minimum value of HFE, the variation of HFE, this is HFE, the variation of HFE with respect to K should be 0, and that when you differentiate it, what do we get? You differentiate the expression, this expression with respect to K, you get the value of K. So when you differentiate it, you get 4 minus 29 by K square equal to 0, or that gives K square is equal to 29 by 4, or K is nothing but root 29 by 4, and that value of K is 2.6. That value of K is 2.6. When you put this, so I get minimum value of HFE minimum, that is equal to 4 multiplied by 2.6 plus 23 plus 29 by 2.6, and that is approximately equal to 44.5. So this is another important value. You have questions in engineering services prelims based on this. So minimum gain of BJT for sustained oscillations should be equal to 44.5 in BJT based phase shift oscillator. That is another question you will find in the exam. Fine. So that covers the complete analysis of phase shift oscillator. I hope you understood, although it was little lengthy topic, but I assume that you have understood the overall expressions and mathematical approach for analysis of phase shift network. But you should remember the formulas directly for handling the objective type questions in engineering services prelims and maybe in GATE. And rest, of course, that approach means what was the approach? We had to obtain beta, and that has to be made real. For making it real, we have put a real component in diameter equal to 0. So that is overall approach of analysis, right? So that finishes your phase shift oscillators. In my next video, I'll be talking about the LC oscillators. That is another important topic. You have questions in exams, so wait for my next video. Thank you very much for watching the video.
To watch more videos like this, subscribe. Click on the bell to turn on notifications. Click on the like button. Share.